morning. Right, so last time we stopped at this example. Let me find that on the notes. Yeah, we did this one. Right. Now we continue on this example. 2, 3. Yeah. Of course, we could do this again, make a table. However, just realize that on section 11.1 and on 3D example, we actually already write the Taylor series for that, and this is what we have. And on that section, what we have is this. Instead of write the polynomial, we're just going to write a few terms. 1 plus 1 over 1 times x. So pretty much that. So we're not going to do that table again. By the way, we did this table quite a few times, so that's why I'm not going to do that again. Now next, use Maclaurin series. For e to the x to write Maclaurin series. Right, now we want to write x to the fourth e to the x. Right, this should be very easy. Actually, we have x to the fourth and then e to the x. We can just use this. Because that one equal to e to the x, and we actually write a series for e to the x, and that is that. So we just multiply by 1 and we just multiply it out. So x to the fourth plus x to the fifth 1/2, x to the sixth 1/6, x to the 7 1/24, x to the 8. So simple enough. If we have that series, if we multiply to it, just multiply to it. Very simple. Now how about we try to write a series of e to negative 2x. Now for e to negative 2x, originally we have if x is equal to that, I'm just going to copy again. So now what we do is we're going to substitute negative 2x into x, pretty much. So e to the negative 2x equal to 1 plus, instead of x, we're going to use negative 2x. Substitute on all of this x. That's simple enough, right? So the point here is, if we have the Maclaurin series, then we can either multiply to x or power of x, or do the computation of this. So that's why you will find this in almost any engineering book. It's just some certain function. I'm talking about the note over there. Some certain function, they have some kind of series, and then we're just working with this series. We don't have to do the table every time, but I just want to do the table just so to get the idea of how this Taylor series works. Rule number 3, convergence. Of Taylor series. I'm just going to write the theorem. So it is convergent if the remainder goes to 0. For an x in the interval where the remainder is defined as this. And C is the point between X and C. Right, so we have that theorem. Now let me just we're going to skip this example. I'm just go to number 4. Some common function, Taylor series for some common function. Highlight this. Alright, I'm not going to write out everything. Right, so it has the series for a bunch of common functions. We have e to the x here, sine and cosine. And let's just write few series, but we just write in the e to the x is the summation of k equal to 0 to infinity x to the k factorial that converge for all x. Psi of x -1 k x to the 2k plus 1 over 2k plus 1 factorial. And there are more. Right. So in real life, these results are very significant because some function that we cannot integrate, in which case we just prefer to go back to this and write out the series, and then we integrate term by term. So this is very common for engineering, where we go to a function that we cannot integrate. In that case, we just look up for the series and then we just integrate term by terms, because after all, if we just want the approximation, let's say we want to integrate this function, we might not need to the whole series. The first few terms will be good enough. So that's why the remainders is important. So we do the approximation. Instead of doing that for the whole series, We just do that for a few terms, and the remainder will tell us how close is our approximation is. So if engineering have the problem that they cannot integrate, they will look up for the series, and they integrate the series, and then from this theorem we can say how good is the approximation is, what is the difference between the actual solution and the approximation solution, and they can actually calculate that very well. So with that we go to section 11.4. See how those series can be done. All right. By the way, when we write this first few things, just to note that now there's another confirmation that sine is an odd function. As you see, this is an odd number and this is an odd number, but most important, because due to the power here, sine is an odd function, and for cosine the power is even. Right. We will not do every problem in this section 11.4. Just get the idea of what kind of problem that we can use utilize the Taylor series. So we'll do one each. Just going to do that first example here to find the limit as x go to 0 x squared plus 2 cosine of x minus 2 over 2x to the 4th. So first of all, this is not x goes to infinity, so we cannot just take the highest ranking or the highest power. Cannot do that because x go to 0. X does not go to infinity. So first, I'll go back and see what is the Taylor series or Maclaurin series for cosine of x. So for cosine of x, it's going to be this. So let's just write that first. So cosine of x is equal to 1 minus x squared over 2 factorial x to the 4th over 4 factorial minus 4, and the factorial will be the same thing. So it's not that bad. That's 1 minus 1/2 x squared minus 1/4 x to the 4th minus 1/6. Plus, wait, this is a plus. The sign is alternating. If we want to, the next 6 factorial, so 24, 6 factorial. If we want another term, 8 x to the 8 factorial, yeah, so those are factorial. 6 factorial is 7, 28 factorial. I don't have a let's not do that. Anyway, so we write the cosine is this, and then we will substitute into this. Use that, substitute into cosine. So back in our problem, back to our problem, x go to 0. We have x squared plus 2, and then the cosine, I'm going to use this, like that. Sometimes if we cannot use the actual function, we use the approximation, and the Taylor series is the next best thing. So the key here is how many terms do we have to write? The answer to that is enough. We just write enough terms. If it's not enough, we can always go back and write a few more terms. Right. Let's multiply it out. X squared plus 2 and 1/2 minus x squared 2 and 24 will be 1 over 12 x to the 4th. 6 factorial is 720. And divide by 2, so 360. 2 and 720 cancel out. And then minus 2 over 3x to the 4th. Right. Now we see that x squared, negative x squared cancel out. Negative 2 and 2 cancel out, and we're left with this. One over 12 x to the 4th minus 1 over 360 x to the 6th, and so on. Now both of them have x to the 4th. I will factor it out. And x to the 4th and x to the 4th cancel out, so we have that divided by 3. Now, since x go to 0, that one go to 0 because it had x squared, right? So put 0 in here, that go to 0, and everything after that will go to 0 as well, because the rest will have the power of x. When x equal to 0, that term go to 0. So bottom line is we have 112 divided by 3. Which is 112 multiplied reciprocal 1/3 multiplied reciprocal is 112 over 1/3 is 1 over 36. So So that's what we can do using the Taylor series. So that's why most of the engineering problem, I mean, pretty much any kind of engineering, they should have this table somewhere, or online, or the book. I have my book, but I left that in my office. Anyway, so if we cannot find for the actual function, which is the exact values, we use the Taylor series approximation, and this time we only use up to that term, because that will be enough. We get the idea after that, and just do the calculation. And this is as good as this, because this problem x go to 0, so anything after that is going to 0. So this is not approximation, but an exact values. So like I said, we can use the series. Sometimes we cut off at some certain point, and then we can evaluate. The nice thing about this is the power series, the power of x. If we have to integrate power is the easiest thing, right? Now, derivative of power series. I skip the next example. Just do some problem here, just to demonstrate what is the use of the power series. So 2, derivative power series. I'll verify that derivative of f of x sin x is, of course we know already derivative of sine is cosine, but this time just want to show that we can actually using the series to do that. So to do that, we need to write out the series for sine and the series for cosine. We can either write out term by terms, or we can use the summation. Let's use the summation. Right, first from that table, let's start sine of x first. I'm just use the summation. That is sine, the series for sine. Simple enough, right? Now I will check derivative. Which means I will take derivative of that summation. Right. Derivative of the summation, I can check derivative term by term. Check the derivative inside. However, what I have is this one doesn't have x in it, this one doesn't have x in it, so derivative only this one have x, so we only take derivative of that. and then we will only take derivative of that term only. Right. Derivative, that is power rule, so we take that down. Original power, bring down the power, and original power minus 1. 2k plus 1 minus 1 is 2k. Right? Now, the 2k plus 1 factorial is 2k plus 1 and then 2k. When we do the ratio term, we do this a lot. And then when we cancel this out, just have negative 1 to the k, x to the 2k over 2k factorial. And if you look over there, it is the series for cosine, right? Yeah, exactly here. So this one is the series for cosine. So it confirm that derivative of sin x is equal to cosine x. Of course, it's no big deal, but the series, it just work out kind of nice. Right. So that is when we do for the whole series. Now we can also do term by term. So that's good though. However, we can also do this. Now if you don't want to write that, we can just say I'm going to write derivative term by term. Now for sin x, all of the odd power, so we start with x minus 1 over 3 factorial x cubed plus 1/5 factorial x to the 5th. Because sine is an odd function, so I'm going to have all the odd term. The first, third, fifth, and 7, and so on. So I start with that. Now taking derivative. I'm just taking derivative of this term by term. Derivative of x is 1. And then x cubed derivative (1/5) 1 over 5 factorial derivative of x to the 5th 1 over 7 factorial derivative of x to the 7. So we have 1 over 6 x cubed. Derivative of x cubed is 3x squared. 1/5 is 1 over 120. Five x to the 4th. And 7 factorial. If we don't know that, we can always write 5, 7, and 6 factorial. And x to the 7, 7. X to the 6. So you can just take derivative term by term and it will work out just fine. 3 and 6 is 1/2 x squared. That cancel out. 5 and 120 is 1 over 24 x to the 4th, and 1 over 6 factorial x to the 6th. Of course, we can keep going. And then that, once again, if we compare to the cosine series over there, that exactly equal to cosine of x. So we can work term by term and we take derivative. Next, integral a power series. Now approximate. Now I use this function, engineering using this function a lot, and we just try to, this example I will use a lot because this function cannot be integrated. By cannot integrate, I mean we cannot write this as some nice function. So the only way we do this is approximation. Right, let's see what is the actual values. Math, so we try to integrate that from -1 to 1. Oh, sorry, forgot to change the section. E to the negative x squared dx. Right, so we have that much. Right, so how could be the approximation? So first we have e to negative x squared exponential function. Let's write the power series for that. E to the x is going to be this. So from the table we have e to the x equal to 1 plus x plus 1 over 2 factorial x square 1 over 3 factorial x cube 1/4 factorial x to the 4th, and so on. Now if we let's just rewrite this. 1 x 1/2 x squared 1/6 x cubed and 1/4 x to the 4th. Now what we do is we have the negative x squared here, so we're going to substitute in for x. So e to the negative 2x equal to 1 plus negative 2x, substitute in for x. Wait, that is x squared, right? Sorry. Yeah, so whatever that is, we just substitute in for x. Right. I'll rewrite this as 1 minus x squared, and that is 1/2 x to the 4th minus 1/6 x to the 6th, and so on. Now instead of integrate that one, approximately we can just integrate this. So that's the idea. If we cannot integrate the function, just find the series and do the approximation. Let's see how it works. -1 to 1, and the function 1 minus x squared plus 1/2 1/2 over x to the 4th minus 1/6 x to the 6th. As you see, yes, 3 factorial and 6 are equal. 3 factorial, 3 times 1 times 2, which is 6. So that is the same thing. And you're right. I mean, this should be a cube. I see what you say. This is what you mean, right? Thanks. So negative x squared to the 3rd is 6. The power is 6. I forgot. This should be a cube. I wrote that wrong. Anyway, so the idea is when we write that as a series, we can integrate term by terms, and that's what we get. So that should be a cube, and of course that should be simple. And sometimes engineering is all we need. It's just an approximation, right? We don't really need to know what kind of this function equal to. So if you want the number that is more accurate, we just have to take like 10 more terms, and that will be good enough. The more terms we have, the better approximation. Here we only have the first 4 terms here. So that idea, if we cannot get the function, exact function, use the power series. That's the next best thing. Right. I said I'm going to skip a lot of stuff here. A lot of example here, because look like we behind on pace. Oh, why is that negative here? Oh, this negative. This negative. This to the first power, so it's negative. Negative x squared cube is negative cube a negative cube is still negative. X squared cube is x to the 6. So that's why it's negative. Yeah. So if it is raised to an odd power, it will be negative. If it raised to an even power, it will be positive. Because even power is positive, odd power negative. So we write the function. By the way, is that what you're referring to, right? Now we're trying to write the function if it is given by the series. So when we have a series like this, we just go back and look for on the table and see which one is similar to it. So on this we have divide by factorial and the power the same. So that look like the e to the x. So for e to the x we have x to the k over k factorial k equal to 0 to infinity. So that's what we have, right? For e to the x. Now this function is extremely close to that. So why don't we just take 1 minus 2t and we substitute into x. And we just have that series. Or we're just going to substitute in this x. Bottom line is when we do that, if this is a function f of t, so f of t equal e to the, we put 1 minus 2t into x. That's what we have. So the key is sometimes if we have the function, we go to the table, we look for the series. Sometimes we have the series, we're trying to go back and look for whatever function that is corresponding to it. So that look like exponential, and so we just substitute in. So that's what we do. So whether we have a series or we have the function, and that table is very useful. Yeah. So when you do the homework properly, you see some of this. However, on test 3 we didn't get to this point yet, so I did not ask anything about related to that table. Alright. Now with that, we go to the next chapter. Parametric and polar curves. So this, the first part will be similar to pre-calculus or even trigonometry. Parametric equations. Definition. Parametric equation specify x and y in terms of the third variable and since we call x and y variable, so we try to call t something else. And that is a parameter. That's an A. Usually refer to time. And the parametric curve, parametric curve describe by the equation consists of the point so the point x, y, x is a function of t and y is a function of t. For t between a and b. Two. Let's go to an example. So pretty much we have x is a function of t, y is a function of t, and we're trying to graph it or trying to find a function. Parametric equation. So x equal to 2t, y equal to 1/2 t squared minus 4, and t between 0 and 4. So what can we graph this? By the way, we can do this on the calculator. Heat mode. Let's for option in the type of the function. We have the function parametric, polar, and sequence. So if we want to work with sequence, we're gonna get there. Polar, do that later. And for now, parametric. So when we set the function in parametric form, you see here we have x, t, theta, and n. So x for the function, t for parametric, theta for polar, and n for sequence. So whatever the mode we set up, the variable here will be corresponding to that. Right. So now let's just graph. First, x equal to 2t. So 2, that button now is going to be t, and then y is 1/2. Let's type 0.5 instead. T squared minus 4, and we have the graph. That's good and all, but let's go to the windows. T go from 0 to 4, and let the increment be 0.01. So we graph, and the graph is like that, right? So we just sketch real quick. Let's see if it can give us the table. So second graph. Oh, nice. We have the table too. When t equal to 0, x equal to 0, y equal to -4. When t equal to 4, x equal to 8, and y equal to 4. So kind of we have the graph. By the way, the reason I'm only use 2 points because we know what the graph of the function look like. Look like that. So let's say we have gone from this point, and then from that point, yeah, because we have the calculator, that's why we have the graph of 0 and -4 to 8 and 4. So the graph look like that, right? By the way, it look like a part of the parabola, and we can do that. Now go back to this. So we have the graph. It's not that bad. The calculator always do that. But here, what we can do by hand: x equal to 2t, and y equal to 1/2 t squared minus 4. So the point here is, if we can show for t, we can substitute in here for t. So divide by 2 on both sides, we have x over 2 is equal to t, right? So t equal to x over 2, and with that we can substitute that into this t. So we will have 1/2 x over 2 squared minus 4 So will give us 1/2 x square square to go to the bottom. So that parametric equation is equivalent to y equal to 1/8 x squared minus 4. Right, so that's why this looks like a parabola, because it is a parabola. Right, let's take 5-minute break. We'll continue at 9:09. Oh, we're back. Sorry, I was on an email when I tried to answer that. Didn't know the time passed so fast. Anyway. What is the last the note for that portion? Let me find. No, I'm sure it is. No, there is sometime in the video. I'm sure. Oh. Yeah, sorry, it is 11.1. Yeah, I actually looked in the note and I forgot to change the section, but yeah. And I actually I hope that you have no problem trying to submit the assignment on eCampus. The reason I prefer that way because when you submit on eCampus, that goes directly to the grade book. So when I open the grade book, I show an exclamation point right there. So I have to check the score. So I have to look at that, and I have to grade it, or otherwise it will not work. Right. Thanks for answering that question. Anyway, we are back. Yeah, I was on an email for that exact same question. I mean, not particular. The sample test. No, the sample test on eCampus. The sample test on eCampus, just to if you can check it, then you can check the final at any time you want. Because, like as mentioned before, there are two options to check the final, either using the responders monitor. So I post a test or the sample test on eCampus that using that steps. So if you can check the test on eCampus and you can go through all of the settings with the camera and everything, if you can go through that, then it's good. You can just after I post the test on Wednesday, you can check it. However, if you cannot take the test on eCampus, you have to be here on Friday for the test. By the way, I will send out an announcement for the final exam. Yes, if it shows the exclamation point, that means I haven't looked at your answer yet. Yeah, because everything I created, like assignment or test, is shown in the grade book. Right. So let's try to graph this function. By the way, there's a pi here and sine cosine. So this definitely have to be in the radian mode, which is good. So radian mode and parametric form. Now we're going to graph 4 cosine of 2 pi t and 4 sine of 2 pi t and we just graph. What the graph is, it looks like an ellipse, but actually it is. No, for responders you have to use the webcam. Have to use the webcam. I don't think it works on your smartphone, because you have to download the browser to the computer and run from it. It runs some special browsers. So it is kind of like Firefox or Chrome, but it is called a lockdown browser, so you can only have one window at a time. You cannot switch from window to window. Yeah, so it is a circle. So again, if we hit Windows, I'm sorry. We only go from 0 to 1. And when we graph, it is a circle. By the way, if we want to see the circle, hit zoom, choose number 5, zoom square. So, square meaning the x and the y, they have the same scale. So it looks like a circle. So how do we show that it's actually a circle? Right. So parametric equation, there will be two. I don't know why I switched a page. When we're trying to turn into parametric equation into just an equation, what we did here is we solve for t and substitute back in here for y. And here I don't want to do that. The reason I don't want to do that, because when we solve for t, we have the cosine inverse, and substitute in here is sound like a mess. However, what we do instead, what we can do instead is we can square both sides. So we have x squared equal to 4 cosine of 2 pi t square y square So we do that, we have x squared equal to 16 cosine squared 2 pi t, and y squared equal to 16 sine squared 2 pi t. Just square both sides. And then when we add side by side, we have x squared plus y squared equal to 16 cosine squared 2 pi t 16 sine squared 2 pi t. Factor out 16 cosine squared plus sine squared. Of course, that is 1. Right. So the key here is try to utilize cosine square plus sine square equal to 1. Try utilize that to eliminate t, to eliminate the parameter t. So when we do that, obviously, because that is not 1, that is 16, sorry. This is inside 1. So we have x squared plus y squared is equal to 16, which is a circle, radius 4. So when we have cosine and sine, try to utilize this identity. In that case, you can eliminate the parameter that way. Right, number 3. Special parametric equation. A circle. For non-zero number. A and B. So if we write the equation x equal x naught plus a cosine bt and y naught a sine bt, this will be a circle, and the circle describe the circle. So those equations, the same thing as this equation. And this circle center at x naught and y naught. The radius is absolute values of a. Right. Now, the circle traverses two pi divided by absolute values of b times unit. Variant b will vary the speed at which the curve unfolds. Right. And a few more things. If B is positive, that is counterclockwise. Negative, that is clockwise. So that's the circle. By the way, the circle, we have this and this, the same number. If we don't have the same numbers here, we will have an ellipse instead of a circle. B line. So this is how we get into a circle. Now if we want a line, By the way, this sentence makes no sense at all. Maybe I mistyped that. So the curve described by the equation is the line, is a line. It makes a little more sense than that. Assume x naught, y naught, a and b are constant. And a not equal to 0. T between infinity and negative infinity. There's something weird happen. First of all, I have my laptop and it run out of power, and then the speed. The stream, the internet reset. I for some reason. It's good. I'm not sure. It did not show how many frames it dropped, so I actually don't know how much time we skip. I'm not sure if it's the internet or not. Probably not because of the internet, but sometimes the software I'm using, I just reset the stream for no reason. Yeah, so that my CPU only about at 30% capacity. Yeah. And the memory is not even 1%. I mean, not even 10%. So should not be any problem. I probably need to update the broadcasting software, but parameterize the curve. Right. So earlier what we did is that we have equation in terms of t, parametric equation. We turn that into an equation of x and y. Now we do the opposite direction. Have the equation. Now try to write that in terms of equation in terms of t. Actually, this will be a lot easier. So for this, usually we just say if we let x equal to t, then we just have that, right? So for this, let x be t, then y equal to 9 minus x squared is 9 minus t squared. That's easy, right? And then the parametric equation, we say x equal to t, comma, y equal to 9 minus t squared. And also, since we let x equal to t, and x between -1 and 3, so is t. And this is the parametric equation corresponding to that. So simple enough, right? Just let one of them equal to t and the other one follows. So let's say we have this. Now there will be a few more options. If we let y equal to t, so we have this equation. If we let y equal to t, the reason that we choose y equal to t because this equation we have x equal to. If we let y equal to t, then we substitute in for y, and we have t minus 5 squared plus square root of t. Simple enough, right? Or we can let y, square root of y is t, if we do that, square both sides, and because of that, x equal to t squared minus 5 plus t. That certainly works. But like I said, if we let one of them equal to t, substitute into the other, that will be easy. Now try to find the linear path. I would try to find the line connect these 2 points where t between that. So let's try to summarize this information. When t equal to 0, we have x equal to -2, y equal to 0, and when t equal to 2, we have q equal to the point q, 0 and 3. Right, so how do we do that? So first, let t and x, we're trying to write the equation. When t equal to 0, we have -2. When t equal to 2, we have 0. We actually can draw it, but let's do this. Slope you remember back in grade school, we used to do that, right? So in this particular case, and then y equal to mx plus b, that is the equation of a line. Yes, but for now we use t and x. So the slope is x2 minus x1 over t2 minus t1. x2 minus x1 over t2 minus t1. So it's 1. So the equation is x equal to 1t plus something and then we can substitute in 0 at t equal to 0, x equal to -2. T equal to 0. So b is -2. So we have the equation x equal to t minus 2. So we check real quick. When t equal to 0, it's -2. When t equal to 2, x equal to 0. So we do that. We have x. Same thing here though. M equal to y2 minus y1 over x2 minus x1. By the way, when we get to Cal 3, there's a much better way to do this. This will be t. Right now, using this equation is, or even in pre-cal, we use the vector form, which is a lot easier than this. Right, y2 minus y1, t2 minus t1. So y is equal to 3/2 t plus b. I do forgot the square here. Sorry. Yeah, thanks. On the last problem, I forgot the square here. Yeah. So y is equal to t squared. Substitute that in there. We still have the square. Yeah, you're right. I should have the square. Yeah. At t at t equal to, yeah, should have the square there. At t equal to 0, put 0 in here. And that's supposed to be equal to, when t equal to 0, y equal to 0. So b is 0. If b is equal to 0, so y is equal to 3/2 t. So we have the parametric equation x equal to t minus 2 and y equal to 3/2 t. And then t is between 0 and 2. All right. D, definition. The direction in which parametric curve is generated. As the parameter increases. Is called the 4. Or positive orientation. Of the curve. And because if it's negative, then that's called backward. It's not really a big deal though. Most important here is, of course, that's just in pre-calculus. What new here is, now we know some calculus and we have to do calculus on it. Derivative for parametric curve. Theorem. If we have x as a function of t and y as a function of t, and let's say the function are differentiable, So x is a function of t, y is a function of t. But if we want to find the derivative of y with respect to x, this is going to be equal to dy over dt, dx over dt. So take the derivative with respect to t for x and for y, and then for x. And because when we divide like this, the denominator cannot be 0. Right, B. Example, find dy over dx. Let's skip the part where we say it's horizontal and vertical tangent. Let's skip that part. Right. First, we have x equal to t and y equal to square root of t. For t greater than or equal to 0. Right. So find the derivative dy over dx, which is pretty much the derivative of x over derivative of y over derivative of x. So or even we can just write like that. So the function y is 2 square root of t. We're going to take the derivative of that over the derivative of x. Square root of t, we can write it t to the 1/2 power. Take derivative. Derivative of t is just 1. That's simple enough. So when we take derivative, 2 times 1/2 t to negative 1/2 over 1. Over 1, we really don't need the denominator. 2 and 1/2 cancel out. We have t to the negative 1/2. That's all we do. Yeah. Of course, for this one, when t equal to 0, that is undefined. So simple enough. Next. So x equal to 4 cosine of t. Y equal to 16 sine t. Right. In this case, once again, we are asked to find dy over dx. By the way, if you wonder why the formula come from, I'll go back to this real quick. Let's look at this one. If we want to simplify this, divide fraction is multiply reciprocal, right? That's why we print it like that. Now, so when we write like this, pretty much we just have derivative of y and then derivative of x as a function of t. So we'll take derivative of y over derivative of x as a function of t. That's simple enough, right? Oh, straightforward. Derivative of sine is cosine, and derivative of x is derivative of cosine is negative sine. 16 over negative 4 is negative 4. Cosine over sine, cotangent. So we have negative 4 cotangent of t. Right. Now, let's look at this. Instead of do it like this, we can always try to do it different way. Right. Now, this is a very useful trick. Earlier we tried to eliminate t. Okay. So if we have this and square both sides, and when we add cosine square plus sine square is equal to 1, and we have the equation that have no t in it. That's what we did earlier. Now what we do here, if we square both sides, we have cosine square and sine square, but not quite, cannot quite add them. So what we do instead is divide by 4. So we have x over 4 is equal to cosine of t. And then y over 16 is equal to sine t, right? The point here is try to get cosine and sine by itself. Why we need that? Because when we square both sides, we have x over 4 square equal to cosine square, y over 16 is equal to sine square. And we can add both sides. Cosine square plus sine square is 1. So we have x square over 4 square 16 plus y square equals 16 squared to 56. Right, so this is a way to eliminate cosine and sine. Try to get by itself cosine and sine, and then square them. Cosine square plus sine square equal to 1. So we have this one. So how do we graph this one? In section 11.4, when we deal with ellipse, then we certainly have that. Of course, with this ellipse. But if we multiply everything by 256, we have 256 divided by 16, so we have 16 x squared plus y squared equal to 256. and then we can solve for y and then take derivative, or we can take derivative implicitly. Differentiate implicitly. So this is car 1. Derivative of 16x squared x squared is 2x, and derivative of y squared is 2y, but because y is a function of x, we have dy over dx. And derivative of 256, 0. So take derivative implicitly where y is a function of x. And we have that. And so we have 32x plus 2y is dy over dx. And we solve for it. Dy over dx will be negative 32x over 2y and negative 16x over y. So the derivative, of course, then you say, how's that related to that? Of course, if we substitute this back in, we get back to that. Y is 16 sine and x is 4 cosine. When we substitute those back in, we should get back to 4 cotangent. So negative x is 4 cosine t and y is 16 sine t. Again, 16 and 16 cancel. We have 4 cosine over sine. We get back to that. Right. By the way, so you really need to know that, because this trick is very important. This we can eliminate cosine and sine that way. Right. Let's take 5-minute break. We continue at 10:09. we really are behind. Right. Let's skip this one. Let's do. It's a lot more interesting, a lot more important, I should say. Find parametric equation for the circle center at the origin with radius generated clockwise with initial point 0 and 12. So there's a lot of way we talk about this. If we're talking about the now, if we just have the circle center, the origin, radius 12, those together give us x squared plus y squared equal to 12 squared. That is the equation of circle. Center is 0, 0 and radius 12. However, that doesn't tell us where the center, where the equation is. Right. So this is what we can do. So this one goes clockwise, right? And that's a key also. Right. Let's go back to the formula. What do we have? That x equal to x naught plus a cosine bt, y equal y naught plus a sine bt. When b positive, counterclockwise. When b negative, this is clockwise. So first of all, if this is clockwise, so b is negative. So in this case, it doesn't matter how fast or slow, so we just choose -1 for b, just for simplicity. And next, the center is equal to 0 and 0, meaning that x naught is 0 and y naught is 0. So put those information together, we have 0 plus a, and then what is a? Also in that formula, the radius is equal to a, I mean absolute value of a. So a is equal to 12. So put them together, we have x equal to x naught is 0, the radius is 12 cosine b is -1, so we just have -t, and y equal to 0 plus 12 sine of -t. Right. By the way, cosine is an even function. And sine is an odd function. So let's write that. Sine is even. I mean cosine is even. And sine is odd. Sine of negative is negative sine. That's why we have this equation. Right, and finally, we need to make sure that it starts at 0 equal to 12. So, what is that point? Right. So, it starts 0. So we're going to let 0 equal to 12t. X equal to 0, so x is 12 cosine t equal to 0. So we have cosine t equal to 0, so t equal to cosine equal to 0 would be this point or this point. So pi over 2, that is. So put this together and this information. So we have x equal to 12 cosine t and y equal to -12 sine t and t greater than or equal to pi over 2. So we start pi over 2 and we're going forward. We have this. This one's easy. If we solve, just going to write that real quick because that's kind of important. Write equation for x and y. So what we have is x equal to t minus 3 and y is equal to t squared. For -2 t, so t is between -2 and 3. So how do we come up from here to the equation of x and y? So this is quite simple. If we can solve for t, we can substitute in there. So we do is, how about we plus 3 on both sides here. So I have x plus 3 equal to t. And we substitute that in there. So we have y t is x plus 3, so y equal to x plus 3 squared. Simple enough, right? So if we can add, if we can solve for one and substitute to the other, we do that. Unless, of course, we have both cosine and sine. The way to do that is isolate cosine and sine, square both side, and turn into this. So when we have sine cosine, utilize sine square plus cosine square equal to 1. If we don't have that, and we just have the equation of t, solve for it. Last point we need to make is negative 2, t is between negative 2 and 3, but x is that. So what I do is I will minus 3 everywhere. So I have negative 5 less than equal to t minus 3 less than equal to 0, and t minus 3 is x. So x is between negative 5 and 0. Right. So that is how we eliminate t and just have x and y. Right. Next, we go to polar coordinates. Now this is exactly what we have in recount. Except later on we'll have some calculus on it. Polar coordinates. Just sit there for a moment. Right. Like that, this is in breakout. So instead of write the point x and y in rectangular coordinate, what we use instead is array, initial rate, and then the angle. So we use r and theta instead of x and y. So I'm just going to draw this instead. Right. So in polar coordinate, what we have is first the origin in xy coordinate, we use the pole. Call the pole is at the origin, and with that we define an initial rate, positive x-axis, and that is called the polar axis. And from here we will form an angle theta. So we have an angle and then we have that distance r. So as long as we have the angle theta and r, we can identify the point here. So this point in polar coordinate as r and theta. And in this case, we define r to be positive. Now, the problem with this is when we have an angle, we can always go an extra revolution and maybe a few more, or we could go back the other way around and have negative. Right? So we have the same representation of the point. Let's just say r equal to theta plus 2 pi. Actually, not only that, can multiply any k to it, represent the same point. As r and theta. K is an integers. So, and if we have the point there, if we go opposite direction here, this point is going to be negative r and theta. So those are opposite direction as that. B. Example. Graph the following polar coordinate. And then give two alternative representation so first we have the point Q, 1, 5 pi over 4. Right. So, for this, of course, we have the graph there, but the second, let me get a compass. Found it. Right. So for this we have a concentric circle. The first one is this circle radius of 1, two, and 3, and 4. So I have concentric circle like this. Let's just say this is 1 and that is 2, the radius that is, and then we just draw the circle. Radius 1 is radius 2. So on this one the point Q is 5 pi over 1 and 5 pi over 4. It is 1, so this will be in this circle of 1. And then 5 pi over 4, that is 225 degrees, so this is going to be this point. And so we go an angle of 5 pi over 4. So that is point Q, right? So just draw a concentric circle and we do that. Right, now let's draw two more representation of the same point. So first what we can do is, if we add 2 pi to it, we go on extra revolution, we still get back to the same point, which is fine. As long as the radius is still the same, it's good. So that is Q, and 5 over 4 plus 2. So we can say 1 and 13 pi over 4. The same representation. Right. So that's one way to do it. We can add another 2 pi to it, subtract 2 pi to it. It doesn't matter. Another way to do that is, what if we take the negative 1? Now, if we go with negative, we will have to go in opposite direction. And this angle is going to be 45 degrees, or pi over 4. Pi over 4. So if we want negative, we're going to use the opposite direction, which is pi over 4, and then go the opposite as the terminal ray. Get back to here. So pi over 4 is that. Instead of going that direction, we go negative, which is the opposite direction to it, and we have this point. So this is another representation, and this is another representation. So one, we add 2 pi, we get back to the same point, or we add a pi to it, or subtract a pi from it, we go in the opposite direction, and then take R to be negative. And the reason I get pi over 4, because 5 pi over 4 minus pi is pi over 4. So if you take back half a revolution, we get pi over 4, and those either way works. Most important though, doesn't matter where we learned or when we learn about polar coordinates, trigonometry, pre-calc, or here. We need to know how to go from polar coordinates to rectangular coordinates. I will summarize as this. We have x equal to r cosine theta and y equal to r sine theta. This should be rather obvious because I'll go back to the note. But if we go to the first page here on 12.12, this is opposite, and we say sine is opposite over hypotenuse. So with that, r is equal to, r sine theta equal to y, and this is adjacent. Cosine is adjacent over hypotenuse, and r cosine theta is equal to x. So x is r cosine, y is r sine theta. And then from the Pythagorean theorem, x squared plus y squared is r squared. And then tangent is sine over cosine, or x over, tangent of theta is y over x, or y over x, or sine over cosine. Right. So we have that. Now if we want to go from polar to rectangular, we use this. And when we use rectangular to polar, we use that. So this one, of course, we want to go from polar, we have x and y, to rectangular, which is x and I should slow down a little bit, even though we are behind. So polar r and theta to rectangular, and this one is from rectangular to polar. Polar is r and theta. Right. So keep that formula where we can reference to. So this is very important. Let's see, what do I have in this section? Oh, it's not that. Yeah, it's still be high, but not as bad. Right, so again, keep that somewhere. So I'm going to write that in this card. X equal to r cosine theta, y equal to r sine theta, x squared plus r squared equal to r squared, and tangent theta equal to y over x. But in the note I have an asterisk here. Yes, there's an asterisk. And asterisk here is make sure that it is in the right quadrant. So I'm going to use that. First example, express the point with polar coordinate in Cartesian coordinate, which is rectangular. So pretty much convert the point in polar coordinate. To Cartesian coordinates. Cartesian is from Descartes, and his coordinate is what we also call the rectangular, or using x and y. Rectangular coordinates. So originally we are given r and theta. We try to convert to x and y. Right, so r is equal to 2 and theta 3 pi over 4. We try to change to x and y formulas here. So that's rather simple, right? X equal to r cosine theta equal to 2 cosine of 3 pi over 4. Cosine of 3 pi over 4 is negative cosine pi over 4. So we have 2 over 2, which gives us negative square root of 2. And y equal to r sine theta (3 pi over 4). Sine of 3 pi over 4 is square root of 2 over 2. Cancel the 2. So the point in the rectangular coordinate, we have x, y. X is negative square root of 2, and y is square root of 2. Right. So we convert from rectangular to polar. Now what if we do it in the opposite direction? And we'll try to convert the point from rectangular to polar. And here we have the point 1 and negative 1. So we do that to polar. Right. First, in rectangular, it's going to be x and y. Polar is going to be r and theta. So originally we are given x and y. To go to polar, r and theta. So first, x is 1 and y is -1. Right, how do we turn this into our antenna? Well, those are the formula related our antenna to x and y. So x squared plus y squared is r squared, and certainly we can get that from here. So x squared plus y squared. So r squared is 2. So take the square root on both sides. Yeah, let's just choose positive. Square of 2. R squared is 2. So r square root of 2. So that's good. We use that to find r. How do we find theta though? To find theta, we have tangent is y over x. Y over x is -1. So if tangent equal to -1, then theta is tangent inverse of -1. So what is tangent of -1? Tangent inverse of -1. Right, what's that? Right, let's keep this in degrees. Maybe we have a better idea. Let's do that again. -45 degrees. Or equal to -pi/4. Right, but is that it? Let's check. The point 1 and -1, x equal to 1, y equal to -1. Now is that -45 degrees? Yes, and that check. Yes. So that point 1 and -1 works. So we have r and theta square root of 2 and -pi/4, which is good. So that how we change from rectangular to polar. Try another point. Now convert -1, square root of 3 to polar. So we go from here to polar. And so originally we have x and y in rectangular coordinates. Convert to polar, which is our antenna. And we still have the same formula that we can use. That. That's better. Alright, so first we have x equal to -1, y is square root of 3. Right, we have x and y. Now trying to find our antenna. We have r squared equal to x squared plus y squared. x square plus y square. 1 plus 3 is 4. If r square is 4, take the square root on both sides. Let me just write this. R square equal to 4, so r equal to 2. It's easy. Now, the next one is less obvious than that. Tangent is y over x. Negative square of 3 over negative 1 square root of 3. Now if tangent is equal to square root of 3, to get back to theta, we do tangent inverse. Square root of 3. And tangent inverse of square root of 3. (60°), which is pi over 3. Right. It's not good though. Let's check. X equal to negative 1. Y equal to negative square root of 3. This is in quadrant 3. And this is in quadrant 1. So that doesn't work. However, what we can do though, we do have pi over 3. If we want this to be in the quadrant 3 like we want it, all we do is just add a pi to it. So theta pi over 3. So if it's not in the right quadrant, we have to add a pi to it. And we 4 pi over 3, which is in quadrant 3. So our answer is r in theta equal to r is 2, theta is 4 pi over 3. So bottom line is whenever we use the tangent to find theta, or we take the tangent inverse, make sure that it is in the right quadrant. If it is not in the right quadrant, add a pi to it, just 1 pi, not 2 pi. Add a pi to it so to go to the right quadrant. Right, so that's good. That's where we convert between opponent rectangular to opponent polar. And we have this formula, and we're going to use the same thing to convert the equation. Two polar curves. Example 1. Describe this point as polar equation. In polar equation. Right, first example, we have r equal to 3. So r equal to 3. That should be easy. The radius equal to 3, so it's just a circle. Radius equal to 3, right? However, if we want this to be in x and y coordinates, remember, you can use that formula. So it is r squared though. So in that case, why don't we square both sides? So if we square both sides, so if r squared equal to 9, and we substitute that into r squared, we have x squared plus y squared equal to 9, and that is the equation of a circle for sure, right? Equation of a circle with the center and the radius is 3. Right, next. What if we have theta equal to pi over 3? What's this equation represent? Right, so when we have theta, so we have tangent of theta equal to y over x. So we just have theta though. So I will take tangent on both sides. Tangent of theta is y over x. Tangent of pi over 3 is tangent of 60 degrees. Right, that is square root of 3. So y equal to square root of 3. Y over x is square root of 3. So we can say y equal to square root of 3 times x, which is equation of a line. So if we write, it is pi over 3 and we have a line. Y equal to square root of 3x. Have r equal to 2 secant theta. Now this is, we can use any of this, any of that. So first of all, secant is 1 over cosine. If we multiply cosine on both sides, we have r cosine theta equal to 2. Because when we multiply this side, cosine cancel out. So it's that. And finally, r times cosine is x. X equal to 2. Of course, it's the vertical line. The vertical line, x equal to 2. And then on the next one, What is R equal to theta? Right. This kind of difficult to describe, so let's just try to draw this. Right. If we want to graph in polar coordinates, heat mode, of course we go to polar coordinates. Polar. And if we want to graph in polar coordinate, let's keep this in radian mode. So radian and polar. Right, good. Now let's graph. R equal to theta. That is theta. Right. So what we see is that. However, if we want to increase the windows, let's say we go from 0 to 4 pi. And let's see the graph again. So it looks like a spiral. If we increase, it will go further and further away from the center. So this is called a spiral. Because as the angle increase, the radius increase, so it go further and further away from the center. The bigger the angle, the bigger the radius, and it get further and further away from it. Okay, I have to do this one before we start. So convert this. I'll convert the equation into rectangular coordinates to rectangular coordinates. Now this is a little more complicated. It's very tempting to say that R equal to 6. R, and if we square it, we're going to have R squared equal to X squared plus Y squared. So it's very tempting to do that, to square both sides. But if we square both sides, we have sine of theta. Doesn't particularly helpful at all. So what we do is we do this little trick. Why don't we multiply an R here? Multiply an R on both sides. R times R squared. And that gives us 6 R sine theta. And R sine theta is Y. So don't square both sides, but multiply R on both sides instead. So I multiply R on both sides, and we have that. And finally, R squared is X squared plus Y squared. So if X squared plus Y squared equal to 6Y, I'm going to move the 6Y over. And what I do is do the completeness square, try to add something. On both sides to make it a complete square. So what we do is we will take half of the middle numbers and then square it. Half of -6 is -3. Square that is 9. So half and then square. So we have half and then we square it. So we have that. X squared is still X squared, and now those three terms together is a perfect square. y minus 3 square, and that equal to 9. So bottom line is what we have is x square plus y minus 3 square equal to 9, which is a circle, center 0 and 3, and the radius 3. Yeah, that part B. Yeah, so that's why I try to write organized, not the problem, and then yeah, it's no excuse to write that wrong. Anyway, so we can write that. So this is equation of a circle. Right. So on this one, if we try to square both sides, it will be very complicated to simplify. But if we multiply by r, it will be a lot better. So later on we will do this, and then we skip this. So probably we'll finish this quickly on Wednesday. And this part is important, the calculus of the polar corners. So we finish that and try to go as far as we can here. But other than that, we run out of time already. So on Wednesday, I will send you the list of the question that you expect to see on the final. There's no more review. So on the homework and review, everything is on my MATLAB already. So there's no more new assignment. And also, I think some of you already sent back the note for the participation, and some of you already did. So it will straight to the grade book. So I can, after I check it, I can put the grade right there. All right. So before I close the stream, do you have any question? No, there will be no final review. Just look for all the 3 review we have and what we have in this part. Like I said, I only give you the list of the question that to be expected on the final. There's no final review. So we only have, like I said, all the homework and review are posted already. If you do all of them, it should be fine. On Wednesday, you have the list of questions will be on the final, so that should be okay too. The core artifact, the extra credit assignment, make sure you do that. And the written note that you send back, you should already have all of that. And also send that back to me. Yes. So if you cannot use response monitor, then we have to take the final on Friday. Yeah. So I will send you the link on the phone. Either use we might use Zoom or something else, because I just don't want to get Zoom bomb. So and actually I got an email from school highly recommend that we don't use Zoom. Yeah. So what we have is it is that what we call the collaborate Blackboard collaborate ultra. So that is in eCampus. And I test that on my phone. It is even better than Zoom. I send you the link and you can all open the link directly. So there's no more software to install. Just click on the link and then actually this is the kind of the software that go with eCampus. By the way, eCampus is also Blackboard. Blackboard is the name, and we call eCampus. It's just for the district use eCampus, but it's called Blackboard. So I send you the link. You click on the link, and it will ask you, when you click on the link, it will ask you, do you allow the phone to use your camera? And then you say yes, and that's pretty much it. And then you can use your phone as a camera, pretty much. Just like I said, there's no software to install. Just click on the link and it works. And it certainly works on my Android phone. I'm not sure if it works on an iPhone, how that goes, but it should be easy. On Wednesday, I will create one and now I'll send you the link. And if you have an iPhone or even an Android phone, just click on the link and see if you can actually get to that. Yes, the phone is used as a camera, but you still need to log into eCampus and take in the test. So the test will be on eCampus. Yeah. So the test will be on eCampus. It's not on my MATLAB. And at the end, right after you submit the test on eCampus, I give you an hour to submit some written work. Some of the questions on the test require you that you have the work to support your answer, and then you send that back in, just like when you submit the note. So everything you send will be sent to eCampus. All right. By Wednesday, I will send you the link, and then let's see if you can get into that with any problem. At the end of Wednesday, I'll send you the link, and then you just click on that link to see if you can get into the software if there's any problem. Right. Right, do you have any other question? If you have any question, just send me an email, or but other than that, I'm going to end the stream here. Oh yes, it's a 45 minutes, but I realized that I'm not sure if you take the picture and then you have to send that to eCampus. So sometimes you have to get the picture to your computer and then from the computer to eCampus. So it may take a little more time, so I give you an hour instead of 45 minutes. If you send from your cell phone to my email, then 45 minutes is good. But I want it on eCampus. I want you to send the work to eCampus, so that requires a little more time. So that's why I make it 1 hour. Yeah, so you have a little extra 15 minutes. So take the picture with your phone, get those pictures to your computer, and then from your computer send to eCampus. I think 1 hour should be enough to do that. Yeah. And I already look at I already make the test. The test only 4 questions that require you send in the work. So 4 pictures sent to eCampus. Right. No, there will be only 4 questions. Only 4 of them. And when you see the test, then you see exactly, I will specify exactly which question that I want you to send the work in. And then when you see the test, you know which one you have to send in. There are 4 of them. Right. So like I said, on Wednesday I will have the list of the question, and that will explain a little. It will be easier when you see the list of questions, and then to see how the Blackboard collaborate on trial works, and then all other things. But you have more idea on Wednesday. Right. With that, I think I will end this video here, or the stream here. Right. Have a nice day.